Yeah, well, you see, it's probably what sort of something with mini crash course by Ashwin Nayak on information theory, and then there'll be a break, and after that, a couple talks of applications of information theory to Hamiltonian complexity and also black holes. So we're starting with Ashwin.
Thanks so much. So, so Umesh charged me with a very daunting task of, trying to compress a vast and interesting research area into, down to 1.5 hours. And I've been spending the better part of the last few days just thinking about, how I could even do it if it was possible. In fact, I first started out listing all the things I thought were interesting, and then I think over the past 12 hours, I've just been hacking away at it so that I could fit it into something comprehensible, so that it would be, more of a course and less of a crash. So what I intend doing, let's see, is it coming on? Is presenting a view of quantum information theory from the point of view of a user rather than a researcher that's steeped in it. And it's also intended for the user, as in someone, as Umesh said, might not necessarily want to dive deep into it, but would still like to understand the basic principles. So okay, maybe I'll just start to use this. So it works. Okay, that's better. So I'll start with some illustrative applications. I just picked 3 applications which were loosely related to the theme of the special semester here. So I'll go over these applications, point out where in these applications is a crucial use of information theory. And then I'll go back and try to fill in all the concepts that you need to understand, or we need to understand, to see how these concepts actually are put to work. So I'll go over the mathematics of quantum information, and this would probably be really the crash course part of this talk. And I'm hoping that most of you are familiar enough with these basics so that my maybe 10-15 minute summary of it would be sufficient to jog your memory. And then I'll go on to talking about entropic quantities. Now, I should really say that unlike what you might imagine, quantum information theory is not a theory that has been fully developed and sits out there for us to learn from, but in fact it's being invented as I speak. So there are new concepts that are being introduced, and especially in the last 10 odd years, that have come to play an important role in recent developments. But I won't have time to go into all of that. I'll fall back on trusty entropic quantities that were first devised with perhaps specific information processing tasks in mind, and later turned out to be useful in many more contexts. And finally, I'll try to summarize what we have learned, and perhaps point to a few questions that still remain to be answered. Okay, so let's move on to application 1. This is a well-known application in cryptography. It's that of privacy amplification. Here we have 2 agents, Alice and Bob, if you wish, who would like to generate a random key that is known only to them and no one else, so that later on they could use it in cryptographic protocols. So imagine that they've actually gone through an initial phase of some kind of a protocol whereby they manage to share n uniformly random bits x. Now, the problem with this string, or with using it directly as a shared cryptographic key, is that potentially an eavesdropper has secured some information about it. And this information could be in the form of a quantum state. So imagine that Eve has stored some quantum state y that is correlated with this classical string x. Can they still, is there any hope of they still being able to distill a secure key out of x? Now, in the classical scenario where the eavesdropper is entirely classical and y is basically some random variable that's correlated with x, this is a well-solved problem. In fact, what they can do is the following scheme. Alice can pick a uniformly random seed z, which is independent of x, and then send this over to Bob, the second agent. And both of them have in mind an extractor, a randomness extractor in the theoretical computer science sense, E, and they both compute the output of the extractor on their raw key x and the seed z. Now, classically, provided the seed is long enough and the extractor is suitable for min entropy of x given y, we can ensure using strong extractors that this key is actually nearly uniform even given the information that Eve has. So Eve had originally y that was sort of garnered from x, and then later on also saw the seed z that was sent out in the open. So even given both of these things, both of these quantities, this output of the extractor would be nearly uniform to Eve. Now, the problem with using the scheme in the quantum case is that this state y is a quantum state that could be measured, could be observed in one of many ways. And the way that Eve measures this may depend on the seed z, on the seed z. Right? So that the final random variable that Eve has, representing the information about x, now is actually could be potentially highly correlated with this output of the extractor. So a question is, well, are there extractors E that are suitable even against such quantum adversaries? Now, this problem has been around for a long time. In fact, it's an integral component of quantum key distribution protocols, and we've known that, for example, using 2wise independent hashing, we could, in fact, obtain secure keys. The downside, yeah.
Is there something you could say to give me a better sense of what an extractor is?
Okay, maybe I'll just write down a statement here. So the condition that we would like out of, at the end of this protocol for it to be successful is something like the closeness of two distributions. The two distributions are one, which is the output of the extractor, EXZ, and this is correlated, this is jointly distributed with the random variables y and z. So this is actually the joint state, in some sense, of the three parties, right? So Alice, Bob, and Eve. This is held by Eve. That's with Alice and Bob. Now, what we'd like is that the output of the extractor be independent of what Eve holds, and not only that, we'd like it to be nearly uniform. So this should be close to, let me call it U, and if this is over k bits, then this is uniform over k. And then we'd like this to be, if you're thinking about classical random variables, we'd like it to be independent, so in product distribution with y and z. So ultimately, the security condition goes as this is less than or equal to epsilon, this distance, and epsilon is a parameter that you could choose for your extractor.
And is there an example that would give me a sense of, it seems sort of, it's still foreign as a, is there an example that give me a sense of how they work?
Sure. So one example is, so let's say you pick, so this is the two-wise independent hashing example. So you pick z uniformly at random from 0, 1 to the n, and the extractor simply outputs the scalar product x dot z, which is the sum I xi zi mod 2. So that's a possible function. And in fact, this turns out to be highly secure. And you could, so this produces only one bit, but you could think of picking a sequence of, such z's, and then producing successive random bits in the same manner by taking inner products. Producing more bits degrades the quality of the extractor, and not only that, the seed that you're picking is, is really long. And what we'd really like is to balance the two, and try to achieve the optimal parameters, meaning try to have the least amount of communication, use the least amount of resources, thinking of randomness as an expensive resource, sort of uniform randomness. So the goal is to achieve the best security parameters with the least use of fresh key. Okay, so as I said, this scheme here, which has been known for a while, is not really optimal. A few years ago, Amnon Tashma showed that a very well-known extractor, one that's been studied in classical computer science for about 15 years now, is also secure against a quantum adversary, provided you plug in the right kind of ingredients into the scheme. Now I won't explain how this extractor really works. I mean, that would take me far afield. Instead, what I'd like to focus on is a piece of the analysis that actually focuses on where the action is as far as dealing with quantum adversaries is concerned. So actually almost all known extractors, and especially this Trevisan extractor, works on what's known as the reconstruction paradigm, which broadly speaking says something of the following sort. If the distance between the ideal distribution and what is actually produced is large, so you start with assuming for contradiction that E is not secure against a quantum adversary, then there is a reconstruction procedure for the initial raw key X. So what is this reconstruction procedure? What does it look like? Well, what it does is it produces using it's not able to do this directly from. I'm not quite sure why this.
No, it is. It's just lowered in.
I see. So it's not able to do this directly from the information that Eve has. It needs a little bit of help, and this, but this help is actually quite minimal. So there's a short string A, which, in the case of the quantum extractor or the analysis for the quantum case, doesn't produce the entire string X, but does something, well, almost as good. And I'll tell you why it's almost as good in a bit. What it does is that given any index for the string X, so anything ranging from 1 to n, and some small number of copies Q or Y, so Y is a quantum state, so you just take a Q-fold product of identical copies of Y. Now, given this state, which is now a composite quantum state, the procedure outputs bit xi with high probability. So probability at least some p. Yep. This reconstruction procedure. So there's an algorithm, not necessarily, in fact, it's not uniform because of this string A that produces this bit xi. Now, question is, why does this give us a contradiction? Well, it so turns out that in spite of the exponential or apparently exponential resources afforded by quantum states, that it is not possible to produce short codes that will allow you to do precisely this. Okay, in spite of this fact that measuring one bit doesn't necessarily, it necessarily disturbs the quantum state that you have, so that it doesn't necessarily imply that you can successively reconstruct all the bits of X. It turns out that the code has to be at least linear in length. And I've written down here a one-line proof that I'll later on fill in after explaining what all the symbols here mean. The upshot is that if the number of quantum bits in the state Y is small, then this here, the short advice plus Q times B is small, but it couldn't have been because it's at least linear in length, right? So it couldn't have been that we could distinguish between these two distributions with high advantage. Yeah?
So where do you get the argument that there exists a short string A such that you can reconstruct the whole string? It seems naively that you might be able to reconstruct one bit of X, but why didn't you get all of them?
Okay, so that'll take me into...
That's a long story. Okay, never mind.
Yeah,
That's more a classical argument.
that's right.
Where does the parameter Q come from? Is it part of the security?
No, so the reason we need copies of Y is because the classical argument, the classical part of this argument gives us a procedure that needs access to the state Y Q times. Now, as I said, measuring a quantum state possibly disturbs it irreversibly, so that you wouldn't be able to necessarily get the correct information each of those Q times unless you had an independent copy of it.
So what should I think of Q as being? Is it constant or?
No, actually, it's not a constant. It's probably polynomial. Toma probably knows better. It could be up to polynomial. So the polynomial in n.
Yeah, I'm not sure. It's not constant.
It's not constant.
You'd like it to be as small as possible, but
Yeah, that's right. Yeah.
it depends on the output length of the extractor.
Sorry, it's probably like polylog n, is it? I forget.
No, it's I think it's some small power.
Also, okay.
You don't want it to be large, but no, they're doing the whole thing.
Right. Yeah.
I think.
Oh, do I need to plug it in? Okay, so let's look at the second application. So this is, this is a topic that's been talked about quite a bit, and it is probably fresh in your minds from this morning. This is about the local Hamiltonian problem, in fact, in one dimension. Here we have n particles all arranged on a line. Each of these particles is a d-dimensional system, and they interact with nearest neighbors. They interact through an energy term, an energy penalty term, Hi, between the ith and the i+1th particles, which is a Hermitian operator that is basically d squared by d squared, acts on the space of the two qubits, and has norm at most 1. A central problem in this area is to understand what are the properties of the ground state of this Hamiltonian H. H, which is the sum of these local terms. Now the ground state is basically the eigenvector of H with the minimum eigenvalue. H is an exponential sized matrix, so naively, if you were to try to calculate this ground state, you would take exponential time. In fact, even if you asked a slightly weaker question, well, maybe a question that's much weaker than asking for the entire ground state, which is basically asking for an estimate of the ground state energy to within a 1 over polynomial additive term, it appears to be hard even for quantum computers. So it's QMA hard to actually estimate this quantity. In fact, it's even hard if you allow these Hamiltonian terms to be all the same, so for the system to be translationally invariant, although it's not quite as hard as this. On the other hand, there's been a very successful tradition of being able to heuristically solve, and more recently rigorously solve this problem when this Hamiltonian is gapped. So what that means is that the difference in the least eigenvalue and the next higher eigenvalue of this Hamiltonian, of this Hermitian operator, is at least a constant that's independent of the length of the system. Now, you've probably come to see that the reason that this happens is because of what's known as the area law. If you looked at a general quantum state on this n-particle system, it could potentially be highly entangled. So if you look at, in fact, an interval of this sort, it could be that each particle inside is maximally entangled with a particle outside. So that, in this example, if you considered an interval of length L, you might have entropy L log D being the entropy, maximal entropy of any one particle. What the area law says is, in fact, that this is not possible when the Hamiltonian is gapped. When it's gapped, really what can happen is that the entanglement only is proportional to the size of the boundary, which is basically constant in 1D. And this result, although was conjectured and believed very widely in the physics community, was only rigorously proved about 7 years ago by Hastings, and then vastly improved in the recent years. And in fact, it's this area law that gives rise to the algorithm that Zev talked about. So So here's a key step in Hastings' original proof that gives us some insight into why such an area law might hold. Actually, really, I wouldn't be touching what I consider to be the key part of this argument, which is perhaps far too sophisticated for me to wrap my head around, but also because, again, it doesn't fall into the theme of my talk. But I'll present at least what you can infer from it once it's once you're given this tool. So here's a high-level outline of what the proof is. Again, the proof is by contradiction. You start with the assumption that there is some interval. In fact, there is some split partition of this line into two parts, let's say after particle I, such that when you look at the reduced state, let's say on the left, it doesn't matter where which part you pick, reduced state of the ground state on the left, then its entropy is high. Now, what that actually implies, as we'll see a bit later, is that the entropy of the reduced states for any cut, so going from particle I all the way up to some I plus m, is also large. Now, the crucial step in Hastings' proof is the following. If you look at an interval within this region I to I plus m, let's say of length L, let's split it into two halves, A and B, and look at the entropy of this joint system AB, so the particles that are in the two contiguous intervals A and B. Let's call that the reduced state rho AB, and then if you focused only on the left half or the right half, you'd get rho A or rho B. Now, if you looked at the entropy of the entire interval, we'll see in a bit what entropy means, but right now just think of it as some measure of randomness or present in the state. It could be as high as the sum of the entropies in its two parts. And morally, what this means is that the state is actually, if indeed it achieves this maximal entropy, then it's a product. It's an independent product of rho A and rho B. So the two halves actually are not entangled with each other or even correlated with each other. So as I said, the crucial part of Hastings' proof is a consequence of the Lieb-Robinson bound, which says that this cannot really happen, meaning rho AB is in fact quite far from the product state rho A tensor rho B. Okay, in terms of quantum computation, what this means is, or quantum information, this means that there's a measurement that distinguishes the joint state rho AB from this synthetic, product of our minds, which is the product of the two reduced states with probability that's exponential in the length of the interval. Yeah?
I generally think about Lieb-Robinson bound in sort of a dynamical picture that correlation sort of spread at some speed. How does that sort of dynamical picture mesh with this implication that you have here that it implies that the entanglement is most of the thing?
That's a good question. If I remember correctly, it basically appears in the form of the decay of correlations, in terms of this length L, the length L of the interval. Maybe that's as far as I'm willing to risk.
I think the dynamical ones are used in the proof of the exponential decay of correlations that you're.
Okay.
But it's kind of the harder stuff.
Right. All right. So what can we conclude, from this measurement? What we'd like to say is that, in fact, the entropy of this interval is not quite as large as this. In fact, it's much smaller. So if you look at this difference, which is the maximal entropy and what actually is, it's constant, it's proportional to L, the length of the interval. Okay, and this gives us a recurrence on the maximal entropy of the state on any interval of length 2L as twice SL minus some linear term in L. And if you solve this recurrence, you get something like L log D minus order L log L. Okay, so really what this is saying is even if these two halves of the interval had high entropy, the entropy arose as a result of entanglement within and not through entanglement with particles outside this interval. Okay, and you can see directly here that if this length L is large enough as compared to the dimension of the particles, you get a contradiction. You have a question, Aaron? Oh, okay.
Where does the gap come? Which step depends on the gap?
It's the
The Lieb-Robinson.
yeah, it's the implication of the Lieb-Robinson bound here. Okay, let's move to the third application. So I'm just throwing a whole bunch of concepts at you and a whole bunch of properties with the hope that once I start explaining what they are, you might begin to understand how they're used and what the principles behind their use are. And in fact, I'll go back to these applications and fill in all the details once we have those definitions. Okay, so here's another application in quantum complexity theory now. So we're all familiar with NP proofs for 3 satisfiability. Given a Boolean formula over n variables. Question is, we know that there is an efficient proof. A small witness for satisfiability. It's of length n. Basically, the prover would specify what the satisfying assignment is, provided there is one. And there's an efficient way to verify this. Question is this the shortest that a witness might be? And it's believed very widely that indeed it is. And the reason is that we basically believe that there are no sub-exponential algorithms for satisfiability. That this is the strong exponential time hypothesis. It says that there is no algorithm for 3-SAT that runs in time exponential n to the gamma for gamma less than 1. Surprisingly, if you allowed quantum provers, not one, but 2 quantum provers, you get a quadratic improvement. So you have proofs of length roughly square root n. A caveat is that these 2 provers are required to be completely independent from each other, meaning they each send to this quantum verifier a state, rho, and sigma respectively, which are in product with each other, in tensor product with each other. The verifier basically takes input the formula and does a suitable computation on this tensor product state rho tensor sigma, and outputs whether the formula is satisfiable or not. In the case that it's satisfiable, he outputs satisfiable with probability 1, so the completeness is 1. But when the formula is not satisfiable, he outputs not satisfiable with constant probability, strictly less than 1. Again, you might wonder how short these quantum proofs could be. It turns out that for the same reason that the classical proof is optimal, the quantum one is also optimal. Well, not for quite the same reasons, but the same underlying belief that there are no sub-exponential time algorithms for 3-SAT. And this follows from a result by Aram Harrow and Fernando Brandao, who gave an algorithm to essentially optimize over, well, something akin to product states over two quantum systems. Now, such an optimization problem is, it's clearly quadratic because you're trying to optimize over a tensor product of two, positive semi-definite matrices. And we don't know in general how to solve such beasts efficiently. So what they do instead is to optimize over a set that quite approximates the feasible region quite well. And the underlying observation here is that product states are what's called infinitely extendable, meaning if you had a state rho tensor sigma over a bipartite system, then you could imagine it as being a part of a much larger state, as large as you wish, in fact, with many copies of the system B, so identical systems B1, B2, B3, B4, all prepared in state sigma, so that if you looked at any pair A, B, I, then the reduced state on this subsystem would be exactly the same as on AB. So it would be rho tensor sigma. That's what it means to be infinitely extendable. Now the main theorem here is this can't be possible for an arbitrary state, rho AB, unless it is close to being product in the following sense. In fact, you can make a quantitative statement of this kind when you don't have an infinite extendability, but only k, where you're constructing a state with k copies of B. So let's say tau AB is such a state which can be extended to tau AB1, B2, B3 up to Bk, so that when you look at the reduced state of tau ABI, it's exactly tau AB. So if you have such a state, then what we can guarantee is that it's close to the convex hull of these the set of product states. Okay, and it's close in this sense, according to some norm. The state that's closest in the set is within polynomial in log dimension of A, divided by k here. So provided k is large enough, if you pick k to be polynomial in log dimension A, and in the case of this quantum proof, A goes as exponential in square root log n, so this is really something like square root log n, so ultimately k needs to be of that order.
Could you show the definition of k extendable again?
Okay, let's go back here. So I showed you, well, this picture is, maybe I'll write it down. I think that's better.
Oh, I see. You never had a definition of k extendable. I see.
I only said it in words. Maybe that's So state tau AB is K extendable. If there is another state tau, so let's say this is over space H tensor K, then if there's a state over H with little k copies of this capital K, this is over the space H tensor capital K to the tensor K, such that the reduced density matrix, so the reduced state, the partial trace.
So what are H and K again?
So these are the underlying Hilbert spaces,
What these are Hilbert spaces?
right?
Okay.
L of H tensor K means it's a set of linear operators. It's a quantum state, so it's a positive semi-definite operator with trace 1.
Okay.
And K extendability means there's another such positive semi-definite operator in a larger space, so that when you reduce it, so let me just say this is, so if you trace out all B except for Bi from tau A B1 up to B sub K, and I'll define these operations in a moment. So this is exactly equal to tau AB. So this partial trace operation takes a state in the larger space and produces a state in the smaller one, and it's a linear operation that we'll see in a moment, and it imposes the condition that the smaller state that you get is what you had before for each I. Okay, so perhaps all I'll say about how this is derived, well, for now, is that it's a consequence of what's known as the chain rule for mutual information and the Pinsker inequality. What's more useful at this point is probably understanding why such a result might hold in the first place. If you look at this condition here, what this tells you, well, let me write this. Let me give this a name, which is tau ABI. So you have these K states. Tau ABI, all of which are identical to AB. Now, if tau were entangled across A and B, or A and B1, then it's it couldn't possibly have the same entanglement with also B. A couldn't have the same entanglement with B2, B3, B4, and so on.
Why? Is this a monogamy thing?
Right. This is the monogamy of entanglement, and
Can you explain that? Why that's
Um,
I'm trying to remember why that's the case.
okay. So I guess basically, in terms of let's see what a good example is. Okay, maybe I can explain it in for classical correlations, right? So classically we know that so if you have two random variables x1, x2 that are jointly correlated with a third random variable y, then this mutual information. So the information that Y contains about x1, x2 is essentially a sum of the information with x1 and x2. So it couldn't happen that all the information, all the correlations that were shared with, between x1, x2, and y came from x1 and also originally from x2. Right? So the chain rule here says I of x1. I mean, this exactly is
X2.
sorry, x2. Right, so this is sort of the monogamy of correlations in the classical world, and a similar property holds in the quantum world for entanglement. Okay, so what does this buy us? Well, so what we've achieved is actually a reduction, or an approximation of an optimization problem, or at least the feasible region for this quadratic optimization problem, by the feasible region for a semi-definite optimization problem, and the function and the objective function is actually a linear function over over the variables. So ultimately, we reduce this problem to that of semi-definite, an STP. And the bottom line is that for a suitable choice of k, which is log dimension of the first space, we can do this optimization in time, which is exponential in this log dimension. And so what this means is, if you had quantum proof that was something like, let's see if I have, okay, so I haven't written it down. So if you had a quantum proof that was n to the half minus gamma long, then you would get an exponential 1 minus twice gamma algorithm for 3-SAT, which we believe is not possible. Okay, so I probably missed your cue for the half an hour. Oh, I have time. Okay, good. Okay. Oh, that's fantastic. Yeah. Okay, so I'm going to. I'm actually going to switch to the board, and I'll consult my slides here so that we can. I can fill in all the steps, and. Okay. All right, so I have about 10-15 pages of notes that I'll probably just skim through. At first I thought it would be good to have sort of a rigorous definition of what the basic elements of quantum computation are, but instead, I'm just going to write down a few things on the board with the hope that once they're put up there, you'll recognize all the elements. So this is the second part of the talk where I'll be talking about what a quantum state is, what quantum operations are, what measurements are, and the way, the simplest way to think about them to be able to understand to a large extent, the properties of the information theoretic properties that go into these three applications. So the kind of state that we are most familiar with is basically a pure state, which is a vector, unit vector in some d-dimensional, complex Euclidean space. But in general, what could happen is you might be studying a composite system, a system that consists of in the case of the 1D area law, we looked at a system with n particles with each of dimension d. So in that case, what we might be interested in is looking at the state or the description of the state of only a part of the system, right? And once you do that, the correct viewpoint for a state is not simply a vector in such a space, but something more general, which is basically an ensemble of states, meaning a probability distribution of these states. And such a thing could arise just more directly, where out of a probabilistic process, and in fact even from a measurement or part of the state, right? So it's natural from a whole bunch of for a whole bunch of reasons. So these are what are called mixed states. This is some probability distribution over such pure states. Now it's highly cumbersome to work with this description of states, even though it's you can do it without any without running into any problems. But there's a much neater, much cleaner, more succinct representation of these mixed states in the form of what's known as a density matrix. The density matrix corresponding to this mixed state is a linear operator, and you construct it as a convex combination of these outer products. Vi with its dual bra Vi. Now this is an operator on this d-dimensional space, and it has really very special properties. And one of it is probably immediately obvious from this description, this definition. If I call it rho, then rho is positive semi-definite. Not only that, it has trace 1. Actually, these two properties turn out to exactly characterize matrices that arise from mixed states. Okay, why is that? Because if you take any matrix sigma which satisfies which is positive semi-definite and has trace 1, and you look at its spectral decomposition, sigma. Look at the spectral decomposition of sigma. All its eigenvalues are non-negative because it's positive semi-definite. And they sum up to 1 because it has trace 1. Right, so morally you could think of sigma as having arisen out of a mixed state where you pick eigenvector u sub I with probability lambda sub I. So that's basically all that you need to understand about quantum states. What about operations? Well, one basic operation is preparing some number of particles in a fixed quantum state. So let's say you have some k qubits prepared in 0. In the state 0. So appending some ancilla, what are called ancillary qubits. So, having introduced this notion of a density matrix, what I'll be doing for the rest of the talk is identifying a quantum state with its density matrix. Now, you might ask why that's a legitimate thing to do. In fact, it's not quite evident from this description, but there are very simple examples where distinct mixed states give rise to the same density matrix. But very powerful property of this representation is that any two mixed states with the same density matrix actually behave exactly the same under the same evolution. So under quantum operations and under measurements, they have exactly the same behavior. So I'll be identifying a state with and writing it always as a density matrix. So this operation here basically looks like taking a state rho and mapping it to tensor product like so. Now another familiar quantum operation is what we all know and love about quantum computation. It's unitary evolution of an isolated quantum system. So have unitary matrix U. Under this map, a density matrix rho goes to U, rho, U adjoint. And this is consistent with our view of how pure quantum states evolve, and correspondingly how mixed quantum states evolve. If you simply write down what the density matrix would be for a mixed state like so, after it has evolved under U, it would look like this. Now the third operation. Well, you might imagine that you have a composite quantum system. So you have a state that is over some d1 plus d2 qubits. And you let the state evolve, but finally you're only interested in one part of the state, so the state corresponding to the first d1 qubits. Is it possible to express the state of the first d qubits only as a mathematical object over the first space? And the answer is yes. There's this operation called the partial trace operation, and you can write it, it's a linear operation on density matrices. You can write it like so. It's basically given by any choice of orthonormal basis for K. So it looks like identity tensor EI. Where EI is an orthonormal set in K. So these are three basic operations, and turns out that any other operation that's physically allowed by quantum mechanics can be derived as a composition of these three. Actually, maybe I should really point out a few things, or at least state them, that these three are examples of operations, and I'll just throw out the words in here and maybe not really explain fully what they mean. So these are all completely positive trace preserving maps. So the second property should be almost self-evident. None of these three things, three operations, actually perturbs the trace of the matrix. It maps density matrices to density matrices, so trace is preserved and it's one. In fact, positivity is preserved, so positive semi-definite matrices are mapped to positive semi-definite matrices, but these three operations actually have a stronger property that they're completely positive, which means that if you're letting a part of a larger quantum system evolve under any of these three operations, then indeed it will be a legitimate quantum operation on the larger system, okay, regardless of how big that system is. Now, something else I'd like to mention about this is that this is a precise mathematical characterization of all possible quantum operations which may be derived by any kind of composition of these three. In fact, any such operation has a very simple form. At the outset, you might be a bit daunted by just trying to reason about an arbitrary composition of these three, but turns out, regardless of what composition you take, you can express it as basically a composition of just three operations. First, appending some ancilla, some suitable number of qubits in a fixed state, applying a unitary, and then throwing away part of the system. Okay, no matter how complicated your original quantum operation was, you can view it as a sequence of those three steps.
So, just maybe a quick question. How does this relate to the Hamiltonian view?
I'm sorry, which one?
The Hamiltonian view?
Oh, the Hamiltonian view. Okay. Well, the Hamiltonian view is right here. Basically, the unitary arises as e to the IH for a suitable Hamiltonian, evolved for a time, certain amount of time t. So U we think of as a discrete operation, or basically an evolution of the Hamiltonian for a fixed time interval.
So it's integrated or something over time.
That's right. Okay, the final thing I would like to introduce before I go on to something more meaty is the idea, the notion of a measurement. Often people talk about measurements as operations that are distinct from these, but in fact mathematically measurements are special cases of quantum operations. So maybe I'll just recap what the most familiar measurement looks like, and then we'll see how it relates to a general quantum operation. So a von Neumann measurement, or a projective measurement, is specified by a sequence pi I, each pi I being a projective measurement, an orthogonal projection. If this is a measurement over space C to the D, so these are all linear operators on the space, such that they sum up to identity. Right, and we all know what it means or what happens when you measure a pure state V according to this measurement. We observe one of the possible outcomes I probabilistically, and we observe I with probability basically norm squared of the part of the state that's consistent with this projection. Another way to write this is as a trace of pi I times the density matrix corresponding to V. The reason why I write it this way is because, for a mixed state rho, this is precisely what the concise expression for the probability would be. Now you might imagine doing a more complicated measurement. So what might that be? You might do some computation, or you might let the state evolve according to one of these operations here. And then finally measure using a von Neumann measurement. Turns out that there is, again, a very neat, succinct representation of this composite measurement, this general measurement, and it's quite similar to a von Neumann measurement. So it's given by what is also called as a POVM. It's a sequence of operators, EI. EI are all positive semi-definite. And of course, they are on the same space, so that they are operators on C to the D. And they also sum up to identity. The only difference is that these may have arbitrary eigenvalues anywhere between 0 and 1, as opposed to projective measurements which have eigenvalues only 0 and 1. The rule that governs what the outcome would be, or what the distribution over outcomes is precisely captured by this trace. So on measuring state rho, we get outcome I with probability trace EI rho. Oops. Okay, so here's a more useful representation of this measurement, this kind of measurement as a quantum operation. And this is how I'll be viewing it. So it's a special kind of operation which takes a state rho to basically a distribution over outcomes. So it takes rho to sum over I over states I, each state I occurring with probability given by the corresponding element EI here. So any such measurement, by the same token as this, the completely positive trace preserving maps having a succinct representation, also have a simple decomposition as basically appending some ancilla, performing a unitary, and finally doing a von Neumann measurement. So all of these things somewhat, should probably explain why we are able to basically precisely capture what the complexity of implementing these steps in our models for quantum computation are. What we try to isolate is basically all the resource requirements, and we try to concentrate them in the unitary evolution rather than in the measurements. So that the final measurements are all very simple. They're von Neumann measurements in a fixed basis state, which is presumably easier to implement than an arbitrary measurement.
I'm somewhat troubled by the very last thing, because
This one here?
because when you do a measurement, you stay in the same Hilbert space, right? You are just putting your state into a subspace. But here, in the last line, you are creating a whole new Hilbert space, kind of like it's like a theoretical concept somehow.
Right, but physically you could think of implementing it as follows. I mean, what you do is, you use some fresh ancilla qubits, implement your old measurement as a unitary evolution where you write down the outcome in the fresh ancilla, so in your workspace. And you just discard whatever happened to the original state, and what you're left with is your measurement outcome. So although that may not be the best way to implement it, in the arguments that I'm going to make, this is mathematically an easier thing to work with.
But then you are losing some information, but you don't care. I mean,
Yeah, for what I'm going to do, I won't care about what sometimes you think of as sort of the residual state after a measurement, like this projected state when you do a von Neumann measurement. Okay, so one final thing about states, and I think then after that I'll have to start zipping through something more information theoretic. Okay, so this final concept is to do with how well you can distinguish two given quantum states. Given states rho and sigma let me define a distance measure on these two states. Define what we'll call the trace norm, or actually better written as with a subscript 1. As the trace of the square root of M adjoint M. So for any matrix M, this is a well-defined positive semi-definite matrix which has a unique square root, and this trace norm, I'm jumping ahead, is basically the trace of this square root positive semi-definite matrix. And what is this? In the context of distinguishing two states, this is a Hermitian operator, which is basically the difference of rho and sigma. This is the trace distance between rho and sigma. Now, how is this related to distinguishability? Well, the way we can access information about states is only through measurements. But it turns out that this trace distance exactly captures how well you can distinguish these two states through measurements. So the maximum over measurements, let's say E sub I, the L1 distance between, so let's just denote by the operation E, the measurement operation that I've defined here. This gives us, two classical distributions. We can look at how different they are in the L1 norm, and it turns out that this is precisely the trace norm between rho and sigma.
Wait, what do you have on the right-hand side?
This here
Yeah.
is the trace norm of
But you
rho
have
minus
sub
sigma.
1.
Right.
Oh,
I'm
it's the
just
same thing.
using the same.
Oh, I see.
Okay, so let me just explain what this is. Actually, I should have said that before. If you look at what this expression is, here, M dagger M is a positive semi-definite matrix whose eigenvalues are the squares of the singular values of M. Taking the square root, we get a matrix whose eigenvalues are the singular values of M. And so this trace norm is basically the sum of singular values of M. And it's a one norm because we are taking just the sum of the eigenvalues. So it's the L1 norm of the singular values. We could define similarly the 2 norm, the P norm of the sequence of singular values, and all of them give us valid norms. But the one that is most relevant to us in terms of distinguishability is this one here. Okay. So I think that gives us enough tools so that we can zip through some information theory, okay, in the last 10 minutes. So as I was saying, entropic measures really, there are no canonical entropic measures per se. It's just that these measures arise naturally when you study different information processing tasks. And one measure that has, time and again come very handy is this notion of von Neumann entropy. Now, this is von Neumann entropy is not this sort of hammer that you can sort of go and smash any old problem in information theory you have with. In fact, in certain tasks. For example, in privacy amplification, the relevant, in randomness extraction, the relevant entropic measure is in fact, min entropy and not von Neumann entropy. And so you have already seen a few examples where, the canonical entropic measures are quite different from the one I'm defining. But nonetheless, this is one that occurs quite often, and in fact, in the 3 applications that I mentioned, figures very prominently. So here's what it is. With the exclusion of others, I'm going to focus on this and quantities that are related to this. For any state rho in d dimensions, this entropy basically tries to characterize the amount of randomness in the state. When I first learned about this notion of, first of all, a mixed state, it was already very confusing because I thought of a quantum state already as having some sort of inherent randomness. But fact is that the randomness arises only when you make a measurement. If you know a priori that a certain system has been prepared in a pure state V, then in terms of ignorance about the state, there is little ignorance. I mean, you know precisely what the state is. So the notion of von Neumann entropy actually is a more, faithful measure of our ignorance about what the state is. So here's how it's defined. We've seen before that you can, using the spectral decomposition, write it as a convex combination. Oops, that's lambda just I. Convex combination of orthogonal states. Von Neumann entropy is basically the Shannon entropy of this vector of eigenvalues of this matrix. Okay, so if your state was pure, then you would have zero entropy. If your state was uniformly distributed over an orthonormal basis, for this it would be log of d, and it could range anywhere in between for general quantum states. The way you might interpret it is very similar to, well, just from this, let's write this down explicitly. It's a sum over I lambda I log 1 over lambda I. Roughly speaking, this is the amount of randomness it's how random the ith eigenvector is. So I'll just write it as this informally, and this is basically an averaging of this randomness. Okay, this is operationally not a very very useful interpretation, but if you take it literally, there's at least when you study area laws, you can see a correspondence between between this sort of view of von Neumann entropy. You've already heard about a few interpretations. So one is, this is the least entropy of the resulting state when you do a complete von Neumann measurement of rho, right? Another interpretation is, well, it's the least number of qubits that you need on average to compress many copies of rho. Okay, it's very similar to the classical Shannon theorem, noiseless coding theorem. Okay, so maybe, so what I'll do is perhaps just, just explain this other interpretation of von Neumann entropy as a measure of entanglement and entanglement rank, and then, and then gauge, or maybe ask Thomas what I should do. We're nearing the end of my time. Okay, so here's so let's say you have a pure state. And when I say a pure state, in the back of your mind, you might think of this as the ground state of a Hamiltonian. And you're wondering whether this state can be represented succinctly, in particular whether its entanglement rank across any partition is small. So let's say this state is V, and it's in a tensor product state. I'm just going to look at one partition, so that I'm looking at space H tensor K. Now, Zev probably talked about the entanglement rank. In the literature, it's also called Schmidt rank. It's also the tensor rank. And this is defined as the least k such that you can write V as a sum of tensor products of, as a sum of k tensor products. There exist vectors AI in H, BI in K, such that B is some linear combination, need not be convex, I equals 1 to K, alpha I, AI tensor BI. So, product state V1 tensor V2 has tensor rank 1. So if you have a state like this, it's clear. A state like so, which is what we call the maximally entangled state. As rank D. There's no way to express this as a sum over fewer terms of this sort. Turns out that this notion of entanglement is closely related to von Neumann entropy. And in fact, this is sort of the reason why area laws are studied and in terms of either quantity. Originally, in terms of von Neumann entropy, but for more, for computational reasons in terms of entanglement rank.
So, just it has to be non-zero.
Oh, you're right. That's right. So, alpha I is
So, but it could be really small, and that still contributes
Right.
the same as a larger one.
yeah.
So, but then it shouldn't be related to the entropy.
Well, if it's the least k, then you don't need that restriction.
Sorry.
If it's the least k, you don't need to impose that.
The non-zeroness of
Oh,
alpha
yeah,
I.
yeah, then it's fine.
Yeah, because you'll
That's
achieve
right.
the minimum with.
Right. But you're right. I mean, it's not exact. They don't correspond exactly. You'll see the the slack.
In one direction.
Right. Okay, so the easy direction is the following. I don't know whether it's easy. There's a direct connection between entanglement rank and this singular value decomposition of matrices through a sort of a simple isometry between bipartite states and matrices. So what this tells us is for any vector V in H tensor K, there are orthonormal sets Uj and Wj in H and K respectively. Such that, and lambda j non-negative, such that V can be expressed as summation j going from 1 to some L, lambda j uj tensor wj. Okay, where L is actually bounded by both the dimension of H and the dimension of K. Now, why is this remarkable? Well, if you look at the way I've defined entanglement rank, it could be as high as the product of the dimensions of H and K. But what this is telling is that that's for at least tensor rank of a bipartite system, it's always bounded by the dimension of the smaller system. And moreover, it has a very special form where both of these left and right vectors form orthonormal sets which are in bijection with each other. Okay, an immediate corollary from this is that if you look at this, the reduced state of V restricted to either space H or K, then its entropy is bounded. Okay, so the entropy of rho sub H, in fact, it's equal to the entropy of rho sub K, which is equal to the entropy of lambda. So the reduced density matrix on either side can be written in terms of these orthonormal sets. So rho sub H equals summation I lambda I sorry. Similarly, rho sub K. The maximal entropy that this could achieve is at most log of L. So at most log dimension of H or K, whichever has the smaller one. All right. So in the minus however many minutes I have, maybe I'll just state the other part, which is, which may not be immediately obvious, but is quite straightforward, which is that, let's just write this here. If the entropy of rho sub H, where this is the reduced density matrix on the H side, is, let's say, kappa, then for all t, let's say greater than 1, V is, let me just not make this too precise, it's close to a state V tilde of entanglement rank at most 2 to the t kappa. And this closeness is, well, maybe I can just write it and not say what it is precisely. Something like 1 minus constant. Okay. All right, maybe I'll just stop for questions and let that guide where I'm going.
So we have questions for Ashwin.
Is there an equivalent to Schmidt conversation in higher, more parties, like three-party Schmidt conversation? Or 4
Sorry, could you repeat the question?
Is there an equivalent to a Schmidt composition in when you have more tensor productions? So if you have 3 parties?
So there is there's a definition of tensor rank for multipartite states, but no similar, similar structure for tensor rank.
I think it's even open, like here the maximum dimension can be n. Is it true? I vaguely remember that it's even unknown what's the maximal dimension of, I think that in R it's not even clear what is the maximum dimension, or am I wrong here?
Leonard's the right person to,
Correct.
and
It's
that's
not- it's
my
just
memory
unknown.
as well.
it's somewhere between, let's say we go to one more party, so three party. It's somewhere, the maximum you can have is somewhere between 3 n squared over 4, 3/4 of n squared and 1/3 of n squared. That's, no one knows. Never. Maybe this is over the complex field, so maybe the gap is between 1/2 n squared and 1/3 n squared in this case.
Right, so what would be the tensor rank for the max? Oh, that's low. The maximally entangled, that would be just n. The I, sum of I, that would be just n. So that's a terrible example. So to go to n squared, you really need a tricky construction, I guess.
Well, a random thing would get you 1/3 n squared.
You have other questions? Yes, let's thank Ashwin again. So now we have a 28-minute break and we